All right, guys, we'll start now. So before we go to today's contents, there are a couple of things to begin with. So we have a Panda Express fundraiser right after this. So we'll talk more about that later. And then today is our final workshop of all the content that we plan to provide. But there'll also be a feedback form for you to tell us more about what would you like to learn more, what would you want to solidify, and maybe after today's workshop, what more would you be interested in? So we can probably go through those contents next week. But today we're going to walk into our last topic in kind of this BCI project stuff. So we're walking into the field of artificial intelligence. And specifically, we are going to look at something called deep learning. And within that, we're going to look at an algorithm, which is neural networks. So let's start with machine learning. And machine learning is the study of algorithms that learn patterns in a given set of data. So we're basically telling a computer to, for instance, recognize a pattern that's probably hard for us to recognize by ourselves. So there are a couple of different algorithms in machine learning. For instance, one of the very simple one would be linear regression. So you can think of this as fitting a best fit curve or a best fit line onto a kind of a data. And there could be an independent variable and a dependent variable. And then you fit a line. It could be linear. It could be polynomial. It could be exponential. But you're fitting a trend. And that would be regression. There could also be things like clustering, where you want to group things into different groups based on different characteristics. So one thing that a lot of people do is they, based on a given set of characteristics and symptoms, they group whether a tumor is benign or whether a tumor is malignant. So that will be clustering. But that can also be some sort related to classifiers. So what a classifier do is it would be classifying whether something is of group 1 or whether it is of group 2. And we'll look specifically at a classifier today. And we're going to be classifying EEG signals. And we're going to classify whether the signal belongs to a patient or whether it belongs to a healthy participant. So why we want to use machine learning, that's because we're often faced with a task that's too complex for our human brain to deal with. We can probably be faced with, for instance, data in 4 dimensions or 5 dimensions that we can't simply picture. We might be facing with databases that are just too large to work with. So that's why we need the help of computer to assist us in the process of machine learning. Today we're going to specifically look at an algorithm in machine learning, and that's called artificial neural networks. And by its name, you can already tell that it is correlated to our human brains, and it's very it's analogous to our neurons. So on the right, you can see a picture of my bad. Yeah. So we didn't miss anything. We talk about machine learning. On the right, you can see a picture of what is described in a neural network algorithm. So in this case, we have 3 layers of neurons. These so-called neurons, they're not actual neurons, but we can put an analogy to it. So on the left, we have these input neurons. And in the middle, we have these so-called hidden neuron or a hidden layer of neurons. And on the right, we have an output layer of neurons. So how we would interpret this, we can think of them as how our nervous system works. So for instance, on the left, we can think of them as our sensory neurons. So we have these neurons to take input, to take, for instance, a stimulus. And then these inputs are going to be passed on to this so-called hidden layer So we can sort of think of that as our relay neurons. And then on the right, we have these outputs. We can sort of think of them as the motor neurons. So what we are actually doing here is that we're taking in information as input in this layer of neuron. We're going to pass on to this so-called hidden layer, and we're going to process it. And then after this process, we're going to interpret it in some ways until we reach our output. And this output can be think of as, for instance, some sort of muscle contraction in our body. But this analogy has to be put into the scope of our computer program. So the neurons, in this case, they would receive the set of computer instructions. They could receive set of instruction from, for instance, a data set. And these neurons are going to pass on the instructions into this hidden layer of neurons. And this hidden layer of neurons are going to process these instructions, these data, and then they're going to form some sort of algorithm. And through this flow of information, we can think of these information pass through these as action potentials in our brain as well. And then we're going to arrive at the output. So some other terms to know in this neural network would be, besides neuron, would be the edges. And these, you can think of these as the arrows connecting from one layer of neuron to another layer of neuron. And these will be the connections between neurons with an assigned weight representing importance. So you see these arrows draw kind of randomly with same thickness, but actually some of these arrows would be preferred over others. That's what we say we address a greater weight. So if we use the analogy of action potentials, some of these action potentials, they are used more often. Some of these neuron connections, they are favored over other neuron connections. So that's how we can image edges. And also these layers would just be the group of neurons. We have from the left, the input layer, from the middle, the hidden layer, and from the right, the output layer. And we'll go to how exactly this will work when we actually go onto our notebook. And next, we're going to talk about how such a kind of a structure of neurons are actually going to help us in machine learning. So after we pass on the information into our input, we're going to process it. And then this neural network is going to give us an output in the form of numerical information. So for instance, it could be a kind of a continuous list of numbers from 0 to 1. And then that will be sort of a indicating the probabilities of whether something is belonging to one group or whether something is belonging to another group. I realize all these stuff are kind of abstracts here, but it will become clearer once we move on to the Colab. And once we input the information into this neural network, it's going to train it. So how exactly does it do that? It's going to adjust the weights on each edge. So it's going to adjust the preference or how it favors each neuron connection. And then after these weights are adjusted, we're going to arrive at an algorithm that takes certain inputs and then pass it on in a certain fashion and then arrive it in a certain output. And this output, for instance, could be between 0 and 1, with 0 indicating one state and 1 indicating another state. And these two states could be something that we want to predict, could be something we want to classify. And training is over when this so-called error is no longer decreasing. So when we input data into the input layer and we arrive at data in the output layer, we can compare what's going to be outputted with the actual data that we know. So for instance, we can know what the true values of these outputs should be, and then we compare it to the output of the neural network, and then we have a way of estimating the error that our algorithm is having. And this error is sometimes called cost function in some machine learning algorithm. And we're trying to lower this error through iterations and iterations. And finally, when it's no longer decreasing at a reasonable rate, we're going to say we arrive at the neural network that we want. We arrive at the algorithm to compute something from input to output. And that's also when we say a neural network converges. And there are a couple of neural networks that we can use. One of the very popular ones, especially in image processing or image recognition, is called convolutional neural network. And the overall aim of this neural network is it's trying to reduce image into a processable form. So what it's trying to do is it's going to pass one image through a couple of filters. And then after it's passed through each filter, it's also going to do something called pooling. That's reducing the size of the image. So through these cycles of filters and poolings, it's trying to reduce the size of the image and then also extract useful features from this image. And this is the part regarding image recognition is probably not that relevant to today's topic, but it's sort of how the convolutional type of neural network is working. And the other neural network is called a recurrent neural network. And that's also something we're going to focus on today. And that's the type of artificial neural network used for sequential or time series data. So what it means by time series data is pretty simple. It's just any data that depends on time. So for instance, we can say maybe the stock prices has a correlation to time, although that's not the only factor affecting the stock prices, but stock prices can be considered sort of a time series data. And our EEG signals or our brain signals in general, they can definitely be considered a time series data because it's measuring those neural impulses traveling down our scope and with variation in time. So that's also why recurrent neural network can be useful in analyzing EEG signals. So what's its output is dependent on the input and also the prior elements in the sequence. So it's different from convolutional neural network in a way that you can sort of picture it as a for loop. So it's going to cycle through each loop, and then through each loop, it's taking some input. It's also giving some outputs, and then each loop's output is going to be functions at each loop's output is going to be functions at the input of the next loop. So you can see this sort of looping or iterating fashion where the data or the weights are passed on from one loop to next loop. And that's also why it's called a recurrent neural network. And I also realized that so far what I've been speaking of are still pretty abstract. And that's true with neural networks because neural networks are essentially what's called a black box. So we don't really know what's going on. So we know what we are passing into it. That's called the input layer. We also know what we want to arrive at. That's the output layer. But we also see those hidden layers of neurons that we really don't know what's actually doing. So that's why we call it a black box. And that's why sometimes or most of the time, it's really hard to actually picture what a neural network is. But we just make use of it and make use of the computer program to arrive at the desirable outcomes. And here are also some problems with neural networks. Aside from that, it's a black box that's very hard to image, very hard to picture. Is that it's very computationally expensive. So we can imagine these neurons passing on information from one layer to another layer. And there can be a lot of neurons in one layer. There can also be a lot of layers. And there can be even more so connections between layers. So that's going to require a lot of computing power. And that's why we say it's computationally expensive. And also the performance is very highly dependent on the training data. So what this means is that the collected data has to be representative of the population of interest. So what that's saying is that you can't take data from one group of people and create a neural network upon that group of people, and then use this algorithm to fit a trend on another group of people, because the data is really representative of that population of interest, and you can't really transmit that from one population to another population. And that sort of, this representative quality sort of leads to the other problem with neural network, is that sometimes it can also be too specific on the population that you are trying to fit, that we can arrive at something called overfitting. And that's saying that we are training on too many parameters, or we're training on insufficient data that leads to the model being overly specific to the thing that we are training. So for instance, we have a target population that we want to model, but our data is kind of limited to only a couple of individuals within that population. And our algorithm is led to be too focused and too specific upon the pattern of these two individuals that it fails to see the general picture. So the problem here is that sometimes it's too vague. It doesn't capture the target population, but sometimes it can also be too specific that captures the information too well. And that's something we need to balance. And that should be what we have to cover about the background of the neural network. And then next, I'm going to give an overview of the Colab notebook. It should be in the Slack already, but today we're going to, it's mainly sort of a conceptual introduction to neural network, because this is, I realize this is probably a very new topic to a lot of people. It can be very hard to picture. So we don't require too many hands-on exercise, which we will try to provide more of those in the future. But today is sort of just a conceptual introduction. So what we are looking at today is a data set of epilepsy. And we're trying to build a recurrent neural network. Here, RNN is recurrent neural network for an epilepsy classifier. So essentially what we are trying to do is that we are given data from different groups of people. Some of them are healthy, some of them are unhealthy. In this case, some of them have epilepsy. And epilepsy is a form of neural disease that it's specifically referring to recurrent seizures. And seizures are referring to the abnormal, excessive, and rapid firing of neurons that leads to neural disorders in our brains. So by now you can imagine that we're going to look at some brainwave that's going to look pretty abnormal compared to healthy adults. And specifically, what this classifier is trying to do is that we're going to be given data from these different groups of people, and we want to see from this data whether we can tell whether this person is healthy or whether this person is diagnosed with epilepsy. And that's essentially what we are trying to do. And also, what this data set is doing is that it's consisting of 5 sets of data, each with 100 recordings of EEG. And we can see the first set of data is saying that it's non-epileptic with eyes open. So it's referring to those healthy participants in this study. And also these participants have their eyes open in this duration of data. And the second set B, it's also non-epileptic. So it's also healthy, at least in the scope of epilepsy, and then with eyes closed. And then we have a third group of data that's epileptic, but interictal. So what that means is that these people are diagnosed with epilepsy. They have recurrent seizures occur to them, but the data taken is in between seizures. So the data is not capturing the time in which they are actively experiencing seizure. And set D is the same as set C. And we also have set E, epileptic ictal. So that's referring to these patients with epilepsy that are actively experiencing a seizure, and we take EEG data within that time frame. Are there any questions regarding how this data set is doing and what we are trying to do today? All right, so for today's demo, we're trying to classify between non-epileptic patients, non-epileptic participants versus epileptic patients in their ictal data. So we can do something. We're definitely going to need set E, which is epileptic, and then we can choose either one of the non-epileptic group. So in this case, we're choosing set A, but afterwards you can also experiment with other groups to see how the machine learning algorithm would be. So the first thing that we do, unlike our previous workshops, we're not importing data from our Google Drive. We're downloading data from a web server. So that's what this exclamation mark and then wget line is referring to. It's sort of a shell command. So it's not actual Python code, but we don't have to worry about it too much. It's basically just downloading the data from a web server. And here, the first line is downloading the data for set A. So it's downloading the data for non-epileptic people. And then we also have set E, that's downloading all the data from the web server for epileptic, so patients. And if you want, for instance, if you want to compare or classify between non-epileptic eyes closed versus epileptic, you can download data from here for set B. And there are also a couple of things that we need to handle before moving on to data processing. We need to unzip this data into a folder. So for set A, we're going to zip it into a folder called set A. And for set E, we're going to unzip it into a folder called set E. And when you actually run this line of code, it's going to take a while to download all the data. We can see that each data is 100, as it says here, it's 100 EEG recordings. I'll make it a bit larger. 100 EEG recordings from, we can see, for instance, set A from 0 all the way to 100. And then here is also, the names are a bit messed up, but we can also see it's from approximately 0 to 100. So after you run this line of code, you should also have these 2 packets of data put into 2 directories on your local drive. So if you click open the file or the folder icon to the left, you should be able to see set A and also set E. And if you expand on either of the sets, you should be able to see all the different individual text files. And we can see that's 100 text file each. And I think it would also be helpful if we can have a look at these text file, which we sort of do later, but we can also directly open one of them. I'll just go ahead and download it. Yeah, so we can see it's pretty simple. It's just a sort of an array of numbers, and each number would be indicating an EEG signal. And then we can see here, we can't really tell anything from this line of code, but after we visualize it and after we run through the classifier, we should be able to tell what each package of code are indicating, whether this patient is healthy or whether this patient is diagnosed with epilepsy. So after we put the data into different folders, we want to import some useful libraries. So as usual, we need NumPy. We also need matplotlib. And here OS is something that we need to iterate through all the data files. And we don't have to worry about these 2 lines of code too much. We just need to know we're using NumPy to process data. We're also using matplotlib to visualize data. And then this TQDM, it's mostly trying to visualize it's just giving a progress bar for us to visualize. It's kind of really trivial here. So after we load our data, we mount our libraries. We want to actually access these data and then store them into our own variables. So what we do here is that we define 2 directories. We define directory for set A. We also define directory for set E. And then that will be corresponding to the directories here in the open folder here. We also define 2 labels. So these labels are purely arbitrary, but we usually set it to between 0 and 1 so that it's easier for our neural network to recognize there are 2 different states, 2 different labels. So in this case, we're setting everyone with set A, everyone within set A, we're giving a label of 0, and everyone within set E, so everyone who's diagnosed with epilepsy, we're setting a label to 1. But these labels are really arbitrary. And then what we need to do is that we're cycling or iterating through all these files that are loaded onto the local directory. And then we are accessing each file. And then we are using numpy.loadText function to get all these text files from the directory into the data structure that we want, which is called label data. So another thing that we can see, we're given them 2 labels, and we're doing that here. So if the file is within the directory for set A, we're giving it a label A. And if the file is within the set E, so if it's within the directory, if it's within this folder, set E folder, it's going to be put into the label data array, but also with a label E. So, and if it's within the set A folder, which is indicated here, if it's within the set A folder, it's going to be put into the array, but also with a label for A. So that creates our data structure that our computer algorithm can understand. So what the computer algorithm will see is that first there's an array of data, and we can see in that text file that will be just a list of numbers, but also there will be a label so that the computer knows what this data is corresponding to, whether this data is representing someone who is sick or someone who is healthy. So that's basically what this function is doing, is creating our data structure so that our neural network can access and then process. And if we run this line of code, it's just printing how much data we have. And then it's saying there are indeed 200 files, and which 100 of them are corresponding to set A, 100 of them are corresponding to set E. And then we can also print a sample data here. So for instance, if we print the first data, it's going to show a list of numbers, and these would be the EEG signals, and also a label. And this label here, 0, is corresponding to label A. So it's saying that this data is belonging to a participant without epilepsy. And if we change the data here, if we change the index here, for instance, if we change it to 100, we can see that it's accessing a different group of data. In this case, it's accessing a data with label of 1. And label of 1 would be corresponding to someone within set E and someone diagnosed with epilepsy. And the next thing, after we import our data and then load our data into our desirable variable, we want to sort of get a better understanding of what our data is, what our data look like. Although we might not be able to interpret it so far, but we can try to visualize it. So what we're doing here is a very arbitrary process. We're just trying to randomly graph some EEG signals. So that's what this random function is doing. We're first importing the random library, and then this line of code, it's selecting a random index within the set A. So we can see it's within set A. And then if the index of the set A is equal to the label, so we're checking if the data within this index has a label of A. If the data belongs to someone that's not diagnosed with epilepsy, we are appending that index, or we're appending that data into a list that collects all the samples that belong to set A. So if we want to walk closely through this line of code, we're iterating it for 4 times. And then, so we only want to collect 4 samples. And then we're defining a current index. And that will be a random index between 0 and the length of our entire data, which is 100 or 200. So we are going to randomly generate an integer. So for instance, it could be integer of 2. And then this line of code is checking whether the data that belongs to this index has a label of A. So for instance, if we look at the data with index of 2, it has a label of 0, and that's corresponding to the label of A. So it's going to realize that this is the data we want. So we append it into the list that collects all the samples. And we're going to do that for 4 times. And we are also going to do that for 4 times for the set of data that collects sample E. So we do all these, both groups for 4 times, and then we can plot these groups to visualize. I'll actually run this. And we can also realize that each time I run this, it's outputting some different random number. So each time I click this, the graph will look somewhat different because it's selecting 4 new random numbers. And simply by looking at these graphs, we can already capture some differences between class A and class E. So we know that class A is belonging to all the participants without epilepsy. And we know that class E is belonging to participants with epilepsy. So does anyone want to maybe make a guess or look at this graph and say what makes these graphs different? Or are there anything that suggests some sort of data might indicate someone is diagnosed with epilepsy? Yeah, it does look more irregular, and it might be hard to see from here. But if we zoom in on the legend or the axis, we can see that all the class A data, it has a vertical axis from -200 to negative or to 200 within that range, or some even have smaller ranges from like -100 to 100. But if we look at the label or the axis for class E, which are patients diagnosed with epilepsy, you can see there's a much larger range of fluctuation within their EEG signals. For instance, the first one is oscillating from -1000 to 1000, which is almost 10 times stronger than this one. And all the others, they also have greater range. And the smaller one even has -500 to 500. So from this, we can sort of tell, we can sort of tell this difference between the set A and set E. But we definitely need a better algorithm to let us more clearly know whether someone is having epilepsy or whether someone is not, based on these set of data. And that's what we need to actually make use of the neural network. But before that, we'll have a little trivia to test a little understanding of the neural network. So if we can go to the link with our usual code, and then we'll have just one simple question. Might be a bit tricky. Does everyone have the link? We should be good to go. Do people have trouble accessing the link? If you can access it right now, we also have the general feedback form at the end. Guess it's not. Yeah. All right. All right, I'll give one more minute for people to catch up. Does anyone still need time to finish off? All right. So I'll just briefly give an answer. So I realize this might be tricky. We're asking whether the neural network is outputting a value 0 or 1 to indicate whether the data belongs to class A or class E. And I think what might be tricky here is that we define a label here. We define label A to be 0. We define label E to be 1. So that might be confusing. But these labels, as I said before, they are arbitrary labels. So when the program is actually computing the results, we're going to look at how the slides here. It wasn't too specific on this, but here we should know that the neural network, the output of a neural network is numerical. So it's outputting something that we can quantify. That's not only it's suggesting how the neural network is outputting data, it's also how the neural network is calculating the cost function or calculating the error. So what we actually run the function, we're going to see later that it's outputting a range of probabilities. So if, for instance, the program thinks that it belongs to set A, it's going to have a very high probability. For instance, like 0.999 for set A, but it's not going to directly output a label that's going to say that's 0 or that's 1. And that's because that label is completely arbitrary, set by us. But what the computer algorithm is only determining the range of probabilities. So one thing, if you notice some sort of image recognition programs, they'll have, for instance, if you feed into an image, let's say it's an image of cat, and then it will be outputting the probabilities of maybe this is cat. If you're feeding a cat, it will probably say this has a 99 probability that it's a cat, but it will also say there's a like 0.5 probability that it is a dog. There's probably a 0.1 probability that 0.01 probability that it's a lion. So that's how the computer is outputting numerical data in terms of probabilities. But it doesn't directly tell you. It doesn't give you the decision that's whether we are looking at set A, we're looking at set E, we're looking at a cat or a dog. But definitely we can take use of that probability to compute something that's more useful. We can, for instance, we can say when the probability is greater than 99, then that's definitely set A, that's definitely, or set E. And that's how the neural network work. And then afterward, Ariak is going to talk about how we actually process the data.
Yeah. So hello, everyone. So Bill gave a pretty good presentation about what the data is and how we can like visualize it. So now what we're going to do is basically prepare the data for analysis with our neural network. So whenever you're creating a neural network, you will always have technically 3 sets of data, right? Training data, validation data, and test data. So basically training data is what you pass through your network in order for you to optimize its parameters, and you're basically using validation. So you're basically using the training and validation data set to kind of like optimize your model to the best of your abilities, to the best of its abilities. And then what you're doing is that you're testing your model using your test data to see how accurately it predicts data as never seen before. I'm gonna take this step by step, but that's just like a high level overview of what we're working on. So first things first, we need to basically split up the data into this training set and this testing set, right? So first things first, you should shuffle all your data because you don't want your model to train only on like set A or only on set E. You want to make sure it has a mix of like epileptic and non-epileptic EEG signals to train on. Oh, okay. Yeah. So yeah, so like I said, you have to shuffle your data and make sure your training data set will have a mixture of set A and set E. And what you're gonna do is basically set aside 80% of your 80% of your total data as your training data set. And then the next thing you're going to do is split your training data set, which is 80% of your like total data, and then your testing data set into, which is like 20% of your total data, into the inputs that you're expecting, and then the inputs that you're going to put into your model, and then the expected output, right? So the way training works, right, is that you input this X train data into your model, and then your model will attempt to optimize its outputs using the cost function that Bill was mentioning earlier within the slides, right? And basically, once all of your training data has been like moved through the model, what you're going to do is basically test your model, see if it works correctly on data it hasn't seen before, and you'll basically be able to validate its like accuracy. So yeah, one thing you're gonna have, so as you can see here, the shape of the X training data would be 160 by 4,097. So we have a total of 200 EEG signals between set A and set E. So 160 EEG signals, and then 4,097 time points. And then for Y train, it's just going to be 160 data points, each of which will be either like a 0 or a 1 to represent epileptic versus non-epileptic. And yeah, one last thing, due to like the nature of the model we're using, we just have to add like an extra 1 to our data in order to reshape it. It's not actually changing the data in any significant manner. It's just to make like the dimensions match up for the API that we're using. So now we're gonna actually build the model. We're not gonna get into like the nitty gritty of like all the math going behind each of these models because it's a lot. So we're just gonna explain like, so basically the way Keras's sequential model building works is that you add layer by layer what you want to be represented in your model, and once that's done, your model will be compiled. So first things first, we want to establish a size for hidden layers. Can anybody tell me what a hidden layer is? It was on the slides. No. Anybody? Yes. Exactly, right? So whenever we have like a series of layers within your neural network, there's, other than the inputs and outputs, you can't really see like the layers in between them, and we need to establish a size for them. So the size of each layer will be 64 neurons, right? So yeah, first things first, we're gonna initialize the model. Because we're using this sequential function to create it, you have to like start with the sequential like function call. The next thing you're gonna do is add an input layer, right? So this input layer is basically just gonna have the shape of one like subsection of your X train data. And it's basically just like, if you're thinking about it as like a workflow or like a series of actions, this is just like loading in all your data into the model, right? Just like preparing it to be processed by your model. The next thing we're gonna do is basically create a long short-term memory layer, which will have 64 neurons, right? Basically, a long short-term memory layer will be, it's a type of recurrent neural network. What makes it different from like your standard recurrent neural network is that it basically uses additional filters and functions to like contextualize previous information instead of like basically like summing up all of your previous information at once. Yeah, this step is actually this step is probably the most important part of the of the model, and you know, it basically allows us to process this sequential data. The next thing we're going to do is add a dropout layer. And basically the dropout layer is what we're doing is actually making our models predictions worse, right? And the reason we want to do this is to prevent this phenomenon known as overfitting. So we talked about overfitting in the slides. Would anybody like to remind me what that is? Yes. Yeah, exactly. So it's basically like the model only works with your training data set and it can't really work with other data, right? And this is kind of like this portion of the model is kind of like designed to like account for it basically overfitting to your data and like basically over analyzing it and taking too much information from it. The last thing we're going to do is add this dense layer, and all this dense layer is doing is basically creating a output from all of the processing that we did in the previous two layers. So because we're sizing this dense layer to 1, as you can see here, the output we'll have a total output of just actually like we'll only have like one number outputted, and then once we're going to take that one number and basically run it through an activation function. This wasn't mentioned in the slides, but basically an activation function allows us to like fully classify like a numerical data point. So a sigmoid function, if you guys have like never seen it before, just give me a sec. So this is a sigmoid function, and basically what's going to happen is that wherever our data point lands on this x-axis, if it's like positive, it's basically going to like trend towards 1, and if it's like negative, it's going to trend towards 0, right? And we want like if we want to like clarify the distinction between 0 and 1, or any type of like for like any two sets of labels, you want to use an activation function to make that clarification more distinct when we're actually analyzing the data. So that's all the layers of what our model is like consisting of. The next thing we're going to do is compile our model. We specified the loss function that we're going to use to calculate our cost and how we're going to optimize our parameters through each iteration of the model. And yeah, we'll just run this and compile it. So that's how you build a model. But obviously, just because we've built a model doesn't mean we've actually like done anything yet. Oh, wait. Oh, crap. No, nothing. I just like forgot to run the previous like code block. Yeah. Yeah, so now we're gonna go on to model training. So this is where the so model training, the industry standard practice is to do something called cross-validation, right? And we're basically going to practice that here. So what cross-validation does is that it basically says, look, I have all this training data, right? Instead of just like running all of my training data through it once, what I'm going to do is basically do a series of like mini tests with this training data set by splitting the training data set into, by taking like a chunk of this training data set and calling it a validation and taking the rest, running it through the model, and then using this like partially trained model on like using this partially trained model on this validation data set in order to basically optimize it further. It's kind of confusing, but if you can see here, what we're gonna do is we're gonna fit the model. Oh crap. Yeah. So we're gonna fit the model by splitting our training data set into this 80-20 split. The batch, actually no, not 80-20. Yeah, it's gonna be an 80-20 split. We're gonna like basically take 20 different portions of the data, and for each like iteration of this cross-validation process, what we're gonna do is we're gonna test it on, like, we're gonna test our partially trained model on each of these like 20 mini portions of our data. And batch size is basically just like minimizing the amount of like data the model has to process at one time. So when you run this, take some time. So a couple of things to note. As you can see, when this is running, our loss value is decreasing as the epochs keep going. And another thing to note is that the accuracy of our model will also like slowly increase. Obviously, it's kind of like stagnating here, but if your model has like a 99% accuracy, that's like a really good sign, right? So yeah, whenever you're training or like whenever you're fitting and training a model, you want to be able to see like your loss decreasing and your accuracy increasing. Are there any questions? Yeah. Yeah, it's another split on top, and the idea is basically you're like running it. The reason we're splitting it, we're doing that first split is because you want to actually test your model on data it's like never seen before, right? Right. So if you just decided to like train it on your entire training data set at once, it will, like it'll first of all, you won't have like as much, it won't have as many opportunities to optimize itself. And also like, you won't be able to like, so there's this other like concept in machine learning called like hyperparameter like tuning. And they're like, so hyperparameter tuning refers to like aspects of the model such as like activation function, the activation function you're using, how like the size of each layer that you're using, how you're like processing each parameter. And we can get into more detail about that in future workshops. But the idea is that by doing this cross-validation process, you will have more time to perform hyperparameter like optimization. Yeah. Yeah, so the way it works is that we feed our data through the neural network, and then it produces an output, right? We compare this output to what we're expecting it to be, right? So that's what the labels are doing, right? So let's say we run the neural network and predicts 0, but the correct answer is 1. So if it sees like, oh, the correct answer is like 1, I need like, it'll be like, okay, I'm wrong. I need to like update my like parameters based on this assumption, right? And then it'll perform this process called back propagation, in which it will basically use its cost function to change the parameters to like basically fit like the answer, fit the correct answer.
Yeah, and it's not one where we're model using the test set. The model isn't updating itself based on the test.
Are you talking about the validation set?
Yeah.
It technically is, because like as you can see here, right? When we're doing like each of these like batch, when we're moving through each like validation set, our total loss function calculation is decreasing, and then our accuracy is increasing. the validation data set is basically like, so the validation data set is basically what allows us to come up with this accuracy number, right? So the training data set, it's basically like you'll get some amount of data, you'll run it through your model, and then the model will be like, okay, I'm ready to like check out this like small piece of like new data that I technically haven't seen before, right? And then we use that model to check this new data and come up with this accuracy number, right? And then once we come up with the accuracy number, we're like, okay, this is not like a good accuracy number, right? We can't like be predicting like we can't be predicting correctly only 60% of the time. So what you'll do is you'll change like, you'll try to like change some of the parameters in a much like larger method. And then you'll like repeat this process over and over again until you get to this like 99% mark. Does that help answer your question? It's technically interspersed, right? So like basically when you say like these epochs basically mean is that we're taking our entire training data set and splitting it into like 20 like small cubes. And then what we're doing is that for the first epoch, we're taking the first 19 cubes, running it through the model, telling the model, okay, this is like what you're going to train on. And then we're asking a model to see how well it predicts the 20th cube. And then the second epoch, what we're doing is that we're going to set aside the second to last cube, take the other 19, run it through the model, and then ask it to compare the second to like analyze the second to last cube. And we're basically using this like iterative process to like improve the model. Does that make sense? Any other questions? This is kind of confusing, so feel free to just keep asking. We have the time. Yes. Yeah, wait, actually, you know. So this is our training data set, right? So basically what we're doing during this like epoch process is that we're splitting it into like a bunch of like tiny parts, right? And then what we're doing, so for the first epoch, we're gonna set aside this part of the data, train the model. Technically, we're training the model and train on this part, and then analyze this part, right? And then what we're going to do is we're basically going to like analyze it, like how accurate the model is, and be like, okay, we need to make some changes, make those changes. And then what we're going to do is going to do the exact same thing again, except, oh, this is a really bad. We're going to do the exact same thing again, except this time we're setting aside this part of the data, right? Does that make sense?
Yeah.
Yeah, so validation is just doing a series of like a bunch of like smaller tests with data the model may or may have not seen before. That's like the idea. Yes.
Make the distinction between validation and test data. Because test data is only at the end.
Yeah.
Right here is all validation.
Yeah. So yeah, you're absolutely correct. So this is validation data, but validation is like equivalent to doing like a smaller test on your model before like it's basically just doing a smaller test on your model to make sure it's like working and like optimizing in the way you want it to. Yeah.
And that will be the training, actual training process. And then this will be the validation. So we can do like a practice exam, and that will be validating, because if we are simply training ourselves, we're simply doing the exercise, we don't have a way to tell how well we might be. So we need sort of do a practice exam, so to tell us how well we are. And then we're going to do that process on and on. We do different sets of practice problems. We do different sets of practice exams until we hopefully we're getting better each time. We're getting more accurate on our validation sets, on our practice exams, and ultimately, hopefully, we develop an algorithm that can lead us a good performance on the actual test that we have never seen before. Hopefully, that can help.
Yeah, I mean, that is a pretty solid analogy. Yeah. Are there any other questions? Okay, cool. We'll just keep it moving. So now what we're going to do is basically, so this is what I was talking about with looking at our accuracy, model accuracy and our model like loss. So whenever you're training a model, you want to make sure your accuracy is like increasing and like going towards 1, and your loss is always like decreasing and going towards 0. Yeah, so now what we're gonna do, like Bill said, is do like the actual test. So what we're gonna do is basically evaluate our model on our test data and see how well it performs, right? And we can print out the results. And what you'll see here, right, is basically you'll get a bunch of like bunch of like values. They're not random values. And the ones that are like closer to, wait, no. Oh, I'm sorry. But yeah, this basically, I'm sorry, I really confused myself there for a second. But one thing you can notice is that when you're evaluating your model, our loss is like extremely low and our accuracy is extremely high. At the end of the day, this accuracy number is like what really matters. And if the accuracy is 97.5%, that means you can like pretty easily like conclude that our model is like working well. And yeah, this is just like the actual numerical values of the predictions that we were making. And yeah, that's pretty much it. Are there any questions about this entire process?
The actual output is between we're not using the word between, we're saying whether the actual output is 0 or 1. And this is our actual, these are our actual outputs. And we can see that if we had we used the words between 0 and 1, we could be correct, because these are a bunch of probabilities between 0 and 1. So for instance, if we arrive at the probability, if you can highlight this line.
Oh yeah, so wait, I got this. Yeah. So for example, right? Right here, it's 0.96, right? And basically this is where that activation function comes in. So when you're, or like, this is what we're using the activation function for. So once we put like the actual model's output through the activation function, we'll get the 0.96 value. And because 0.96 is really close to 1, the model will come up with the final conclusion of the number 1, which I think in our case represents epilepsy. Oh man. Great. So just to clarify. So yeah, so set E rep is our data from like epileptic patients. So if the model is coming to the conclusion of 1, that means it's concluding that the EEG signal was from an epileptic patient, right? On the other hand, if the model for some reason is like predicting 6.65 times 10 to the negative 4, that's a number that's really close to 0. It will basically conclude that the answer is 0, and it'll compare that label and like conclude that the data it was presented was from a patient who did not have epilepsy. But yeah, you usually don't want to like you can like look through this raw data, but at the end of the day, the 2 most important like numbers you should be looking at whenever you're doing like a machine learning like model are this loss function is this loss value and then this accuracy value. Well, accuracy is straight up the value of like the number of times the model gets it correct, like percent wise, right? Loss, on the other hand, basically represents the final like numerical value of the cost function that your model is using to optimize itself, right? So the thing is, I could, in theory, like, I'm not going to do it right now because I'm not sure if it'll work, but let's say I change the loss function to something else and like I change the optimizers to something else. This loss value can change, right? And basically you, in theory, you want to also like try to minimize this as much as possible, right? So if you can figure out a way to minimize your loss even further, that also implies that your accuracy can be even higher. The idea is that they're both correlated, but they're determined by like different factors. Exactly, right? So one thing to keep in mind, right, is right here. So when we're shuffling, it's gonna be a completely random, right? So yeah, it's a randomized method. So we're gonna like have like different results. One thing you can do if you want to like check if your model's working across the same, working the same across like all your team members, is that you can do like, I think np.random.seed, right? And oh wait, I didn't import numpy, but and then what you'll do is just basically put in a bunch, like a random number. It has to be the exact same random number if you're like want to compare with your teammates. And then if you put in this exact same random number, in theory, it will shuffle the data in the exact same manner. Yeah. That's pretty much how it works. Yeah. Yes, but which is like a good thing, obviously. But yeah, that doesn't always happen. If you're like getting like a 95% higher accuracy, that means it like basically predicts it. Are there any other questions? Yeah. I'm sorry, can you like speak up? Yeah, you're basically just gonna like classify it. So if it's like really like close to like 0.5, but it's like slightly bigger, just be like, okay, we'll just like round up to 1. At the end of the day, what this is doing is just straight up like rounding. It doesn't like, so that's like one of the flaws with like some machine learning models, and that's like kind of the reason that you want like so that's like, so one issue with some ML models, specifically the activation function that you use, right, is that you can't like account for like these like edge cases that really can't be like classified either way, right? So it depends case to case, but the thing is, for this model, most values won't drop in that 0.5 range, right? Because if you can see here that although like it's like both of these signals are very noisy, you can like tell that there's much more of a pattern to the class E data set compared to the class A, right? So there's like a pretty clear distinction. When your data is like much more messy, that's when your activation function and like figuring out a way to distinguish those like edge cases becomes more important. Yes. Yes. Okay, I might have to like look into it more, because honestly, I don't think I've like set seeds pretty often, but I'll get back to you on that. Any other questions?
I want to address a couple of points that you guys mentioned. So, for example, the accuracy. So we have here a very small data. So you have 100% accuracy. Very wrong, but it's not. You're not going to get anything accurate to the level. So here we use different data. And favorite that I think the original. We have really possible for model to get all of those people. That's how it's specificated. You got 100% accuracy. We get the same model. If we have a lot more people, or we're going to keep that percent accuracy. About the then the next company then we could group to get a high possible accuracy. You need to put none of the data in like the real world. So those are the huge of the flaws of the model. And that is for the networks, any additional requirements. I'm going to do a couple of
Wait, what? Can you repeat that?
that it doesn't have to be a multiple of 1/20. So the accuracy is an infinite decimal number for each one of those.
For any like run of the model, really.
Are you looking at the, so what cell of the code are you looking at?
92. Yeah, that's a good point.
Okay, I think that for that, because we are still looking at batches.
Wait, the batch size.
So here, like the batch size has all the parameters in this function. So that might be the reason. And not 100% confident about that. Not gonna lie.
There are 40. Yeah, I was about to say.
Okay.
Yeah, that's what I was gonna say. 97.5 is just.
Okay. Are there any other questions?
Yeah, so there's going to be 40 data points in your test set and then 160, not data points, but 40 data samples and then 160 data samples in your training. Yeah. And that's like 80-20 is like standard, but in theory, you can like do like train your data on like 70% and then 30% for like testing, or you can do like 90% training and then 10% testing. But 80-20 is like considered like industry standard.
Also, another point about that is very important, guys, when your actual projects is that all of these workshops, we don't put data that is already collected and submitted for us. So when you actually do a data collection, that will provide for us quickly. You'll see that the data is basically like discrete time points. And you have to yourself and segment it into. But here we have 100 data report. 100 tables. Third number of data tables. That's why they need to make sure you do the same, because once you're gonna have to data collection, you'll just get a huge array of data points, and then yourself, depending on the purposes, send them down into consistent to be able to do this computation. But there will not and maybe for
That ties back into the whole concept of why we're using this LSTM layer, right? Because at the end of the day, our data is like sequential, and it's not like we can pass in like time independent data for like an EEG signal. So you need to use like an LSTM to process like the sequential data.
Any last questions? We'll go to a couple of announcements. The most important one is that our F22 and instruct right after the end of this workshop to get the video. If the 20% of your need to go directly to the club, so you can take action learning, that's really depends on learning that you pay for your email, or go directly to the club, which goes back to you. So when and we're going to be available. Again, I have the nature comment. I think the thing we were have to pick up today. Unfortunately, due to the rest, all the people that are proposed for habit or completing both areas, next Monday, with really my management, that I look at the so exactly the thing that we have in our academic record. So very BCIT applications that are available week after our last workshop. So that will be due a week later, Monday and week 9. So there will be a couple of questions that you have to answer, and the key point is that you have to answer them in bullet point style. So don't write long paragraphs in text. Please make sure that all your answers are in bullet points. We'll make sure to mention that in the app, but please make sure to do that. Again, the interviews will only be for people who are interested in being a team lead or who have managed more than 2 workshops. And those interviews will be held throughout week 9. We are currently hoping to have a team onboarding meeting sometime week 10. So that you're able to meet with your team members and you're able to create your group chat and start brainstorming ideas over winter break and before we're able to start the project's week 1 of winter quarter. Finally, we do have a feedback form that will serve as the attendance sheet for this week's workshop. And this form will have more questions this week because we're hosting our last workshop of the quarter next week. And we want to specialize it and individualize it for your needs. So there are specific questions about what you'd rather have us cover, whether it's something that is new that we haven't covered yet in this quarter, or if it's a previous concept that you would like us to cover again and go into more details into. So please make sure to take the time to truly write down your needs because we want to tailor this last workshop to whatever you want. And please make sure to fill it out here
because we'll have to close this form for minutes.